Hello, sir. So essentially, this Python notebook demonstrates a project on 3D object localization using a technique called LiDAR camera fusion, which is very relevant to our computing with signals course. We are essentially taking signals from different sensors, a camera and a LiDAR, and we use a third sensor also, GODS sensor, the GPS sensor, IMU sensor. We'll see how these sensors are used and how the 3D space and how combining them to understand where objects are in 3D space. So first, this is the pipeline. We detect, we fuse, and then we associate. We detect using 2D cameras. We fuse this 3D LiDAR points on those 2D cameras, and then we associate depth through this fusion. First, we will download the Skitty dataset. Uh, this gives us real-world signals like images, LiDAR scans, and calibration data. Then we import the necessary Python libraries. OpenCV for image processing, NumPy for numerical operations, Panda for data handling, Matplotlib for plotting, and PyTorch for detection model, object detection model. We also import a helper function, which is used for transformation essentially for the data for the LiDAR data points into 2D spaces. We'll see how everything being used. First, we get into the data overview. We have four cameras, as I was saying, two grayscale and two RGB. One LiDAR sensor. We'll be using one camera sensor and a well-known LiDAR sensor and GPS and IMU systems. As we can understand, RGBs have a RGB camera have a 15 frame per second buffer, and GPS and LiDAR have a 10. We use the lowest one, obviously. I think this okay. This is 100. I think we have to use the lowest one, 10 hertz LiDAR sensor to accumulate all the latencies and stuff to calibrate together. So the data files are stored in PNG text and bin format. We also a key concept in computing with signals when dealing with multiple sensors is to understand the coordinate system. Now let's get into the reference frames and coordinate systems. As you can see, the camera, the LiDAR, and the IMU each have their own way of defining XYZ. To make sense of the data together, we need to transform the signals into a common element. We use some mathematics to do this. I have researched this. I have gone through how these work. Essentially, we are using a single transformation matrix which account for all the four transformations that need to accommodate. So through this transformation matrix, we first transfer LiDAR to camera, and then using the reverse transformation matrix, we can use it to transform camera to LiDAR. Similarly goes with IMU to LiDAR as well. Once the transformation is done, we need to now the loading has to be. Now the loading camera calibration data and the LiDAR also, right? So this is where the calibration data comes in. These are load text files. Calibration data points are intrinsic matrices, essentially. These cells load text files containing calibration parameters. Think of these parameters are crucial for signals themselves. They define the geometric relationship between the sensors. Okay, now let's get into the functions that we used. For example, we load projection matrices for the camera and rigid body transformation matrices that tell us how the LiDAR is positioned and oriented related to the camera and how the IMU relates to the LiDAR. And similarly, T-Well Cam2 and T-Cam2 Velo, transformation from Velo to Cam2 and Cam2 to Velo. Essentially, using this calibration signals, we then compute the overall transformation matrix. For example, T-Velo Cam2 will allow us to take a 3D point to a 2D image plane, and then the opposite goes. So let's get into the object detection pipeline. Here, now for the object detection part, we are using YOLO V5, which is a stock model. A pre-trained deep learning model to process our image signals and identifying objects. Actually, we could restrict this to cars, trucks, objects, people, etc. But V5 is a good model. It's faster. So this loads the model from PyTorch Hub. Essentially, this is the loading and everything. Okay. Uh, so there are a few functions that we need to discuss now. Detection for the detection pipeline. First, let's get into get detection coordinates, right? For the get detection coordinates function is the main driver. It takes an image and a LiDAR binary file path. First, it runs the YOLO model on the image signal to the 2D bounding box. Next, it will use to point project B velocity B into UVZ plane. Then it processes the LiDAR signal project, we loads the raw 3D points, performs a crucial signal filtering step, removing the ground plane using the ransack algorithm. And in these projects, the remaining 3D points into a camera's UVZ space using our transformation matrix T below cam 2. Now we use get CV UVZ centers. The get UVZ centers is a function is where we associate the 2D detection with depth. For each detected object, it finds the center of the 2D box and then searches for the closest projected LiDAR point in the UVZ image plane. The Z value is basically zero, but whenever it finds a point or something, it assigns a value to it. It's not zero, but it's empty, okay? The Z value of the LiDAR point is then assigned to the object. This is a simple way to fuse information from 2D signals to 3D. Now we'll see this in action. As we can see here, now we are testing this pipeline that we have derived. As we can see here, the original camera images with YOLO 2D detection, the numbers on the boxes, these numbers detect the depth in meters from the camera derived from the LiDAR signal. Below it, you can see the LiDAR points as well. LiDAR points projected onto a empty image. These are color coded to give the perception of depth. Next, we do some sanity checks to see if everything is right and working, essentially debugging the code. And then this is where we use the GPS sensors that we were talking about. Essentially, we use a map and then we see where the coordinates, we get the latitude, longitude, etc. And then we find these points. And these points will be mapped onto a 2D plane. We'll see this 2D plane. We are reconstructing this 2D plane into something more understandable. So this is the overall image that we derived for a single frame for frame 10. I think it was for frame 10. And to do this with the whole video, we can loop this around. We can do the same thing. So for the video, I have taken 100 frames. So at a 10 FPS, I'm using 10 seconds to get 100 frames. And this, as we can understand, the result video has a 100 frames with a cam of with FPS of 9.65. And the result video looks something like this. It has a RGB data with a depth perception and XYZ coordinates. And there is UVZ as well. And then we use this to do this for a video. We'll see how the video pans out. I've already trained the video. I just have to show this video. Just give me a second. So, yeah, there's a 10-second video. There's 100 frames. As you can see, it's working fine, but we can improve it. That's where the elaboration one comes in. This is quantitative evaluation metric. We'll see how this is being used. So basically, we are converting this, whatever this image, instead of this having lost the data, we'll retain this data using a bird's eye view function. Uh, while visual inspection is useful for a computing with signals perspective, quantitative evaluation is key. We typically calculate metrics like 3D intersection over union and average precision, which would require detailed 3D ground truth tables. We haven't implemented that here, but it's an important consideration for assessing performance. So for the bird's eye view visualization, the elaboration creates a bird's eye view map. The create BEV map function takes the raw LiDAR signals, projects the 3D points onto a 2D top-down grid, and color signals by point height. This gives a very intuitive spatial representation, as we can see, of the scene. The red dots are detected objective points, object centers. This is another way of processing and visualizing our 3D signal. Next, we run into a modified pipeline with a redefined depth associations. This is used to we then generate essentially this is the video generation part. We can I'll show you the video generation results as well. There are some videos that first the normal LiDAR stackman, there is a LiDAR stack redefine, and then there is a for the frame time, B mark for frame time. And after this, there is a voxel downsample function, divides the 3D space into a grid and represents all points under each small cube voxel by a single point. Usually their average. This is like a pooling technique. This is a form of spatial filtering and data compression. This was used to see how the compressed data, because it's very important for an autonomous vehicle to make the decision very fast. So for which the processing speed has to be faster. So for which we don't need all these points. We can downsample them. As we can see here, okay. As we can see here, just give me a second, sir. Okay. We use a size point 2 as our metric, and this reduces it to 7,000 from 115,000. Essentially, the speed to downsample took 2.5 seconds, but the time for BM map is 18 seconds, but this took 2.5 seconds. So essentially, this was very fast. Finally, for a more advanced signal processing topic, we implemented a simple 2D Kalman filter for object tracking, detection object positions from frame to frame. Can be noisy. The Kalman filter is a powerful tool for estimating the true state. In our case, position and the velocity of a dynamic system from a series of noisy measurements into a classic time series signal processing technique. We define a Kalman filter 2D class, which has a predict and update steps for each detector object we want to track. We maintain a Kalman filter instance. In each frame for each frame for the existing track, the filter predicts the next position. Then when new detection come in, we associate them with the existing tracks and update the filter. We'll see this in action now. I have already did this training, so we'll download this MP4 format and see this in action. See, this is using the previous command. As we can understand, this is very continuous. It has an understanding where the objects are. These numberings are random, indexing the cars. Basically, this is our car. So this is the final project. So to conclude this project, walk through building a LiDAR camera fusion pipeline and then elaborated on it by incorporating several computing with signals concepts so that we taught in class. From basic signal transformations are fusion to filtering techniques like Ramsack, algorithm, and voxel downsampling. And finally, time series state estimation using Kalman filter. Each step helped us to better process, interpret, and visualize the sensor signals to understand the 3D environment. Thank you for giving this opportunity, sir. Thank you.